Hey everyone, today we're going to be learning how to convert numbers between our basic number systems. Our number systems include decimal, binary, hexadecimal, octal, and BCD, or binary coded decimal. Before we can start converting numbers, the first thing we have to understand is the bases for these numbers, which I have defined here by these little subscript numbers next to the names. What those numbers mean is the number of different digits in your number system. So for binary being base 2, the number of different digits is only 2. And those two in binary are 0 and 1. All of these are going to start at 0. Decimal is the system that we use to count in our daily lives. Decimal being base 10 starts at 0 and goes all the way to 9. When you think about the number 10, that becomes two digits, 0 and 1, which are just reused from those first 9. So it's only base 10. And we have octal being base 8, that uses 0 through 7. And then hexadecimal being base 16, uses 0 through 15. Only what happens when we get to those double digit numbers is we switch over to letters. So what's going to happen is A is going to be 10, B is going to be 11, C is going to be 12, D 13, E 14, and then F for 15, which is the final digit in hexadecimal. So, I went ahead and put a number up on the board here. We have 137 in decimal, and we're going to start just by getting that to binary. We have to follow this flow chart anywhere we want to go. So, if I've got a number in decimal and I want to get to binary, that means I can go straight there. But if I wanted my decimal number to be in hexadecimal, I would have to go to binary first and then go up to hexadecimal. So we'll do that a little bit later. For starters, getting this into binary, we have to draw out our binary number line. Binary number line starts at 1 and just consistently doubles each time. So, if I go ahead and put that up here, I'm going to have 1, 2, 4, 8. It's going to keep going, but I'm going to stop once I get to a number that's greater than my number here, 137. Okay, 16, 32, 64, 128, and 256. So we made it. 256 is larger than 137. So what we're going to start doing is taking our 137 and subtracting these number line numbers from it, and doing that all the way down until we reach 0, and that will give us our full binary number. So we cannot subtract 256 from 137. So I'm going to fill in a 0 for that spot. Zeros on the left side of your binary number are irrelevant. You can actually just erase that if you want to. I'm putting it there for demonstration. If I do 137 minus 128, that's going to leave me with 9. So, since I actually subtracted that 128, I'm going to put a 1 in that place. Now, I cannot subtract 64 from 9, so I can put a 0 there. I can't subtract 32 from 9, I'm putting a 0 there. 16 from 9, same deal. 9 minus 8 is going to be 1. I'm putting a 1 in that place since I did that subtraction. I only have 1 left, so the only thing left here is a 1. So 1 minus 1 equals to 0. So we did it. Our binary number, here base 2, is going to be 1, 0, 0, 0, 1, 0, 0, 1. And that's it. So now we've got our decimal number in binary. Now what if I wanted to take this a step further? We can take this binary number and go ahead and put it into octal. So I'm going to get this stuff out of my way so I have a little bit more room. I'm going to rewrite this binary number over here so we can do the functions for octal. So here we go. 1, 0, 0, 0, 1, 0, 0, 1. Base 2. Make sure you keep that base on there so that we know what number system we're working in as we're working. Converting the octal from binary is simple. You start from the right, come over 3 digits and divide that up. And then from there, go 3 more digits and divide that up until you run out. What I'm going to do here is I'm going to start filling in my number line, 1, 2, and 4. And once I hit this barrier, I'm going to start that over again. Another 1, 2, 4, and then 1, 2. Notice I don't have a 4 here. Even if I filled this in with a 0, the 4 above it wouldn't make any difference to our ultimate number in octal. Like I mentioned, that number, if it's a 0 on the left of your binary number, it's irrelevant. So now all we have to do is add this up. So anywhere you have a 1, you want to take that number and add it with any other number you have a 1 there for, and then bring it down. So here we just have 2, so our first digit is going to be 2. Here we just have 1, so our first digit is going to be 1. And here we have another 1, so we're going to have 2, 1, 1, base 8. So that is our answer in octal. Now, if I come over here, I can do another one, coming back from binary to hexadecimal. So, rewriting my binary number, 1, 0, 0, 0, 1, 0, 0, 1, base 2. Converting from hexadecimal, or converting to hexadecimal from binary, is really similar to converting from octal, in that instead of grouping them into 3s, however, we're going to group them into 4s. So if you start from the right, come over 4 digits, and then 4 more digits, that's it. We just have these 2. So now we're going to fill in our number line again, only now it's 1 space longer, so it's 1, 2, 4, 8, 1, 2, 4, and 8. And again, we're going to add these up and bring the digits down. So here I just have an 8, and here I've got 8 and 1, so that's going to be 9. So it's 89, base 16. So now we've taken this decimal number, put it in binary, hexadecimal, and octal, all right here. Easy enough, right? What if we went a different direction? So we'll take this stuff out and start with a whole new number. So what if I wanted to start in hexadecimal and I wanted to get a number in decimal? Easy enough. So we just take a hexadecimal number. In our case, we're going to use F2 for an example. Remember that the letters represent numbers that are double digits, and F is going to be equal to 15. So we're going to put our base 16 there. When we converted from binary to hexadecimal, we grouped into 4s. Here we're going to break these 2 digits out into a group of 4 for binary, because we have to go to binary before we go to hexadecimal, right? So this and this are going to be their own individual groups of 4. So I'm going to kind of divide them up so you can get a visual representation of what I mean. So if we do a number line over here that's 4 long, it's going to be 8, 4, 2, and 1, 2, 4, and 8. So now we just got to figure out what each of these are going to be. 2 is going to be easy. It's going to be 0, 0, 1, 0, because all we need is 2. F is a little bit more. It's going to be 15. We know that, or 15, yes, we know that. So it's going to be 8 plus 4 is 12. So plus 2 more is going to be 14, and then 1 more is going to be 15. So our total number in binary is just, when we take these and put them together, it's going to be 1, 1, 1, 1, 0, 0, 1, 0. So now if I want to take this number and put it in decimal, just make sure you know that's binary. If I want to put this thing in decimal, I'm going to draw out the full scale number line again over top of this. So it's going to be 1, 2, 4, 8, 16, 32, 64, and 128. And all we're going to do here is add each place that we have a 1 in. So our equation is going to look like this: 128 plus 64 plus 32 plus 16 plus 2. Whatever that equals is our decimal number. So I'm going to work that out. 32 plus 16 plus 2. So I got 242 base 10. That's our decimal equivalent of F2 from hexadecimal to decimal. Now there's one more thing on this number line that we haven't touched on yet, and that is BCD, which stands for binary coded decimal. Now that we're in decimal, you can see that BCD corresponds directly to decimal. Everything else when converting has to go through binary. BCD is the only exception. And I will show you how we'll go ahead and get a BCD number out of this 242 that we just got. So, I'm going to take this away after I rewrite it up here. We are at 242 base 10s. Now I'm going to take this out of my way. Basically what BCD is a binary code 4 digits long for each of these individual digits of this number. It won't be the same as our binary number, which is an equivalent. Instead, it's just a broken down version of this number. I'll show you what that means. When we do BCD, we take each of our digits and we're going to have to make them an individual group. And these groups are again going to be 4 digits long, kind of like we did when we converted hexadecimal to binary. So again, filling in our number lines 4 digits long, up to 8 each time. We just have to figure out what each of these is going to be. This is the only time where the leading zeros make a difference. You have to keep them for BCD because it has to be in groups of 4. So 2 is going to be 0, 0, 1, 0. 4 is going to be 0, 1, 0, 0. 4. 0, 0, 1, 0 for this final 2. And this is our answer in BCD. If I go ahead and take these barriers out of my way, I want to leave these spaces between these groups of 4 to help me differentiate them. And I'm going to assign it subscript BCD. And we just converted from decimal to BCD. So now we're only left with one thing that we haven't done yet, and that is going from octal to binary. So I'm going to get this stuff off the board, and we can do that. Alright, my number in octal, I'm going to do 167 base 8. And just like hexadecimal, instead of going from binary to octal where we grouped it in 3s, now we're going to break each of these digits out into 3. So our 7, 6, and 1 are all going to be their individual group of 3. So let me grab these other markers so I can make it a little more clear. Divide it between each digit. Do a 3-digit long number line for each, so that's going to be a 4, 2, and 1 each time. We just got to figure out what each of these are. So it's going to be 0, 0, 1. These zeros are going to end up irrelevant, but that's fine. 6 is going to be 4 plus 2, so that's 1, 1, 0. And then 7 is going to be 4 plus 2 plus 1. All ones. Notice how octal being base 8, 7 is the largest digit in this thing. We group into 3s because 7 is 1, 1, 1. The next number up in the binary sequence would be 8, which would be 1, 0, 0, 0. So since octal can never touch that, there's no reason to group up into anything larger than 3s. You saw the same thing with hexadecimal where F was 1, 1, 1, 1 for 15. 16 isn't in the hexadecimal system. There'd be no reason for a 5th digit. That's why we use 4 there. But this now, that we've done this, is our binary number, which we can get rid of these 2 leading zeros and just write it back out as 1, 1, 1, 0, 1, 1, 1, right? And now we can go anywhere we want with this. So for our finale, we'll go ahead and solve this for hexadecimal, decimal, and also BCD. But I'm going to start with hexadecimal. So start from the right, group into 4, and then you have these left. Go ahead and sign your number line, 1, 2, 4, 8. Start over past the barrier, 1, 2, 4. And now we just start adding these up. So we know that 4, 2, and 1 all together is going to be equal to 7. And then again, we have 4, 2, and 1. So this is going to be 77 base 16. Easy enough. So now if I want decimal, rewrite my binary number again because we have to go from binary to decimal. It's going to be 1, 1, 1, 0, 1, 1, 1, base 2. So here we have to sign our number line all the way to the end. So it's going to be 1, 2, 4, 8, 16, 32, and then 64. So again, we're just going to add every place where we have a 1. So it's going to be 64 plus 32 plus 16 plus 4 plus 2 plus 1. So 64 plus 32 plus 16 plus 4 plus 2 plus 1. I got 119 base 10. That's our number in decimal. So now, let me kind of define our borders here. If I wanted to get this into BCD, I just got to send these into groups of 4. So let's go over here, the middle, and the right. Split them up as good as we can. Group of 4 is going to be 8, 4, 2, and 1 for our number line. So 1 is obviously just going to be 0, 0, 0, 1. We've got another 1, 0, 0, 0, 1. And then a 9 is going to be 8 plus 1, or 1, 0, 0, 1. And this is our final answer in BCD. 0, 0, 0, 1, a space, 0, 0, 0, 1, a space, 1, 0, 0, 1, subscript BCD. And that's it. That's how you convert from each of these number systems into each of the other number systems. I hope this helps. Have a good one.